Hi, welcome guys. Yeah, so hope you guys have seen my ring theory lecture. Yeah, so we already finished the most basic one. I mean, for the undergraduate, I think it's most abstract algebra is already enough. Yeah, for the some common ideal, a common idea like maximum ideals, the integral domain and quotient rings and the Euclidean rings, and also principal ideal domain and the unique factorization domain, and I already mentioned. Okay, so next we will talk about the polynomial ring. Okay, so polynomial ring is the most important part. The most important part in the ring theory. Okay, so remember that so I think the great picture is that we start from group theory, and then the ring, and then we get a polynomial ring, and then we get a field, and then we get a Galois theory. So this is the usual step. If you want to, if your goal is to try to learn the Galois theory, then you should follow this step. Right? So probably it's not a good. It should be a 1-year course, right? But in my YouTube video, I only talk about the most important step. So I don't talk about detail. I don't talk about some many examples. Yeah. So just summarize. Okay. So polynomial ring. Yeah. So I want to talk about polynomial ring over fields. Okay, so very simple video. So definition. So let's say you can just write P of X to be A0, A1, X up to A n X m, and okay, Q of X divided B1, B2, B1, and Bn X n. Okay, so yeah, so this is okay. So sorry, I'm stupid. So F of X is F bracket X is defined to be A1, A1X up to An Xn, and all AI belongs to a field. Okay, so this is called the polynomial ring over field. Okay, and so we need to define addition, right? So polynomial addition is just the usual polynomial addition. So usual means that go back to your high school, right? So just add it, add. That's it. Okay. Or if you want me to write a detail, I can define a P plus Q of X for each term. Let's say I write it as C1, C0, C1X up to CTXT. For each I, we have a CI equals to AI plus BI. If there's no such I define 0. Okay. Okay, and I also define, you can define a product, right? The product polynomial. If you have two polynomial, f and g, and you just times it, and you see your high school. So high school. So you just do it step by step. Okay. So I don't want to write details. Okay. Okay. Also, so you should check by yourself that that F bracket X is a ring. Also, I should write a commutative ring with identity. So identity is just the 1, right? 1 is just identity. So 1 times any polynomial become that polynomial. Okay. Okay, so let's talk about degree. So if you take a polynomial in this, and the a is non-zero. So the largest non-zero element, the largest non-zero given a polynomial P of X, the largest if the largest power such that an is non-zero is called this n, is called degree. So I define degree P of X to be n. Okay, so stupid example, x squared plus x minus 1. So the degree of this, let's say this f, degree f is just 2. Okay, so let me just write down. So for non-zero constant, so if you have non-zero constant polynomial, so you give me a non-zero constant, let's say a is non-zero. The degree of a I define to be 0. Okay. Okay, and the theorem. So degree of f of x times g of x will be degree of f of x plus degree of g of x. Okay, so proof is just exercise. Okay, because I think it's very intuitive, right? You take the largest to largest, and you it will produce the largest, right? So if this is degree xn, this is degree xm, right? Their product, the total largest power will be xn plus m. Okay, so yeah, trivial by yourself. Okay, so the corollary. Okay, so this corollary is important one. Okay, so if f or g a non-zero polynomial, it tells you that the degree of f less or equal to degree f times g. Okay, so the proof is that you start from here, right? Because degree of f is degree of f plus degree of g, right? And the degree of g is also always greater or equal to 0. Okay, so proof is done. Okay. Okay, so from here that we know that f bracket x is an integral domain. Okay, so simple proof. So if you if you give me two non-zero polynomial in f of x, non-zero, then their product must be non-zero. Okay, the reason is that the degree products must be degree f plus degree g, right? And both are greater than 0 because it's non-zero. Okay, I mean there's a case that this is too constant, right? But f is a field, right? So if f or g are only constant and non-zero constant, then the product must also be non-zero. Okay, so you can focus on one of it must be actual polynomial, at least a linear polynomial, right? So that means one of the degree must greater or equal to 0. So you always non-zero, okay, by this form. Okay, so that means the degree of f of x satisfied degree. So degree of f of x is an integer greater or equal to 0. Also, degree f is less or equal to degree fg. Okay, so it tells you that this degree f should view as the function of the Euclidean ring. Okay, so it gives me hint. Hint what? F bracket x is a Euclidean ring. Okay. Okay, so yeah, Euclidean ring. Okay, so the final theorem is called division algorithm. Okay, so once you have this division algorithm, then you can directly prove that the f of bracket x is actually a Euclidean ring. Okay. Okay, so yeah, so this tells you that if f and g is non-zero, and there exists the polynomial t and r belongs to bracket x, such that f is gt plus r, and r either r0 or second is that the degree r less than degree g. Okay, so this is the division algorithm. Okay. Okay, so I should sort of prove just basically from high school, right? But yeah, but actually, in order to prove it, you need to use the induction. Okay. Let me see whether I should write a proof. Okay, let's write the proof. Well, because I think I think this proof is straightforward, but let me just make a record. Okay, so suppose degree f less than degree g. If degree f less than degree g, then nothing to prove. Okay, the reason is that the reason is that if degree f less than degree g, then we just put t equal to 0, right? So r of x will become f of x. Okay, so in the degree f less than degree g. Okay. So all we need to show is that all we need to focus is degree f greater or equal to degree g. Okay. Okay, so suppose f of x is just something a0 plus a1x up to am xm, and you get some g of x, which is a b0 b1x up to bn xn, where am is non-zero and bn is non-zero, and m is m greater or equal to n. Okay, so let's just define f1 to be f of x minus am divided by bn xm minus n g of x. Okay, so what this means? So this means that I use f1, right? Define f to cancel this term, right? I cancel the largest term. I times bn divided by am. Am divided by bn times sm minus n. So leading term of this xm cancel. So degree f1 that's equal to n minus 1, right? So you can prove by induction, right? You can let me see. Okay, so you can prove by induction. So by induction, you can assume that f1 is t1 g plus r, where r is 0 or degree r less than degree g. Okay, but obviously that this f1 is just f minus am divided by bn x minus n g equals to t1 g plus r. Okay, so which tell you that f is just am divided by bn xm minus n plus t1 g plus r. Okay. Okay, so we can put this is just another t. Okay. So now we have f is tg plus r, and by definition, these are all polynomial ring, and the r still becomes 0 or degree r less than degree g. Okay, so the proof is just using induction. Okay, so one might think this proof is stupid, but you can I will left you to think why field is important. Okay, so from here that we know that degree f is just what we want as d of x in the Euclidean ring. Okay, so that means a polynomial ring with the field as coefficient is a Euclidean ring. Okay, so this is the important proof. Okay, so any Euclidean ring is a principal ideal domain. It's a PID. Okay, so who is the prime element? Okay, so this is not easy, right? But let's define. So I define P of X is called irreducible. Irreducible means that P cannot be written as okay, so let's maybe define this. Let's define. So let's say P of X is irreducible in field of X, means that there exists A of X, B of X, both in a polynomial ring such that the P of X is A of X times B of X, and the degree A greater than 1, and the degree B greater than 1. Let's see here. Right, so this is called this is just follow the Euclidean ring, a general Euclidean ring. So if in general Euclidean ring, so if an element is not prime, means that you can write it as a two products such that they're greater or equal to 1. Okay, so so that means if P of X is irreducible, so that means you just reverse this definition. Irreducible means that if you can write P of X into A times B, then one of it must be constant, right? So one of it must have degree 0. Okay, so it means just a non-zero constant. Okay, so this is irreducible. Okay, so let's talk about examples. So this is very interesting example. There are a lot of interesting examples here. So for example, if I take x squared minus 1, which is written as this, right? So that means x squared minus 1 is reducible in real, also in Q, also in C. Okay, but how about this? X squared plus 1 is irreducible, right? In R of X, because you cannot factor in R of X, and it's irreducible also in Q of X, right? If you're talking about rationals, there's no rational, but it's irreducible in C of X. Okay. So working in different field will lead to different results. Okay, so for example, x squared minus 1 is irreducible in Q of X, but reducible in R of x, because one can write x minus square root of 2 and the x plus square root of 2. Okay, so that means a working different field will lead to different reducible property. Okay, so we have final results. I just write down. So we already developed general Euclidean ring, right? So that means the following two are trivial, right? So any polynomial in f of x can be written as the product of irreducible polynomial. Okay, so this is first fact. The second fact A is if you define f of p of x is a maximum ideal. So remember that we proved in a Euclidean ring, the ideal is always principal ideal domain. So it's generated by a single element. If that element is a maximum, if it's maximum ideal, means that the p of x is irreducible. Woo. Okay. Yeah. So I think that's enough. Okay. So another, yeah. So remember that any maximum ideals, you quotient any maximum ideal will lead to a field, right? So for example, if you take a rational x, q of x, quotient x squared q minus 2, right? This is irreducible in q, right? So this is maximum ideal, which leads to this, which tells you that this guy is a field. So it's a field. Okay. Okay. Yeah. So you can check. Yeah. Let me just let me just write down another results. Basically, it's very easy from algebraic geometry. Okay, so from the fundamental theorem of algebra, you know that any polynomial ring, any non-zero polynomial in C of x has a root. Okay, so which tell you that any polynomial besides except for degree 1 cannot be maximum, right? So which tell you that the maximum ideal of the complex C of x, this polynomial ring must be a form of x minus a, for a is a complex number, right? So basically, I'm used to the same, right? Okay, and then you can check by yourself if you quotient C of x by any x of a. If you quotient C of x by x minus a, then this is the same as you plug x equals to a, right? This is isomorphic to C. So which is this a field? So we tell you that this is a maximum ideal. Okay. Okay, so that means the maximum ideal of the bracket C of x is just is C itself. So it tells you that a set of maximum ideals of C should be viewed as isomorphic to C itself. Okay, so if you start from here, then you can get a hint of the algebraic geometry by looking at the ideal of the polynomial of some general ring. Right, so take any rings, you can collect all ideals, like prime ideals, maximum ideals, and then check whether and then try to put a topology in it. If you try to make it, then it becomes algebraic geometry. Okay, see you guys in the next videos. Bye bye.